In this video, I'd like to work through a few more optimization examples. We'll call this video optimization 2, which is our third lesson for this week. Before we get too far into it, though, I did want to bring up this little scenario that's at the very top of our handout here. If a student wishes to minimize an objective function on a closed interval, but finds that it only has a single local maximum, so a picture of the graph might look something like this, maybe a graph on a closed interval forms this shape. Well, clearly our first derivative is 0 here, and our second derivative is negative, concave down, but that would lead us to believe that we found a maximum value. Our objective might be to find the minimum value. So where do you look along this red line to find the minimum or the solution to the problem? Well, let's not forget that on account of the EVT, not only do we investigate the critical points within the closed interval, but we also have to introduce or investigate the boundaries or the endpoints as well. So if we need to find the minimum value on this particular example, we know that it's not here. Our first and second derivative test leads us to believe that this is a maximum, even if we didn't have a picture to look at. When we found a maximum here, we would then move to investigate the endpoints, and certainly the minimum value would occur here at this end, even though the derivative is not 0. I don't think we're going to actually encounter that with these examples today, but it is worth noting that if we don't find our solution nicely like we have in the last few examples, it would be a good idea to check the endpoints of our domain or the endpoints of our interval. In this example, we have a rectangular flower garden that has an area of 30 square meters. So this portion of the diagram is 30 square meters. And we've got a walkway that's 1 meter wider in one direction and 2 meters wider in another direction that surrounds the garden. What dimensions of the garden minimize the combined area of the garden and the borders? Well, hopefully you see the word minimize and you realize that that should lead us to our objective function. And the objective function would be the combined area of the garden and its borders. Now, certainly we could try to find the area of the garden. Well, we know that that's 30. But then we could also find a formula for this unusually shaped area surrounding it and add 30 to that. That would be our combined area. But in all honesty, it would be easier to recognize that the combined area of this entire shape is quite literally the length and the width of the outer dimensions. So as far as objective goes, I'm going to say that the objective is to minimize the area function that is defined as length times width. Well, now let's consider our constraint or constraint functions. We should recognize that the area of the garden itself is 30 square meters, and the garden has a length and a width as well. And so what we're limited to, and again, this numerical value is helping us identify our restriction, what we're limited to is knowing that the garden area, 30, must be equal to x times y. And as we've done in the prior examples, we can solve for one variable. We might say that y is equal to 30 divided by x, and that's all well and good. But let's also recognize something here. Our objective function was not written in terms of x and y. Instead, we had used L and W. So in addition to this constraint function, we might want to note that the length of the total area is equal to whatever x was plus 4, and our width is whatever our y value was plus 2, because x plus 2 on either side makes x plus 4, and y plus 1 on either side makes y plus 2. And so it's these functions, L, W, and y, that are going to be used to rewrite our objective. The area function for our objective, of course, could be x plus 4 times y plus 2. And again, since we still want just one formula, or I'm sorry, a formula in terms of one letter, I might write this as x plus 4 times 30 over x plus 2. And we've now utilized all three of these constraints, all three of these limitations. Well, now we can turn our attention to the objective function and find the derivative of it. You might be tempted to FOIL this together to avoid the product rule for derivatives, and I think that would be a fine attempt if we didn't have this quotient inside of this second binomial. So with that quotient there, I think it's just going to be easier to find the derivative of a with respect to x by using the product rule. So the product rule says to take the derivative of the first function and multiply it by the second function, and then add to that the first function times the derivative of the second. And we've seen this pattern before. The derivative of 1 over x is negative 1 over x squared. So with that 30 acting as a coefficient, if you will, we now have negative 30 over x squared. A little bit of algebra can clean this up. We now have 30 over x plus 2 plus, or minus rather, as we distribute this 30 over x squared into both of these terms, we'll have minus 30 over x, because 30 times x over x squared is just going to be 30x, and then minus 120 over x squared. Well, that's interesting. This 30x take away this 30x is going to be 0, and what we're left with is now 2 minus 120. I'm actually going to write it this way for emphasis here. Minus 120 times 1 over x squared. And what I notice is that these two terms have a common factor of 2, so I'm going to get that out of the way. 2 times 1 minus 60 times 1 over x squared. And if I'm considering when does this function equal 0, well, this 2 doesn't produce a solution, and now all I need to worry about is when does 0 equal 1 minus, and I guess this wasn't much of a benefit after all, so I'll write it as 60 over x squared again. When does 0 equal 1 minus 60 over x squared? I'm going to add 60 over x squared to both sides of the equation. And now if I cross multiply, I know that 60 is equal to x squared, and then finally x is equal to positive or negative square root 60. Now in all honesty, we don't need to consider this negative square root of 60 because we can't have a dimension of a garden that's negative the square root of 60 units in length. So we're definitely only going to consider the positive square root of 60. So we think we found a solution. That's where the first derivative is equal to 0, but as I had kind of alluded to up here, it's possible that we find a first derivative that's equal to 0 that doesn't actually, in this case, represent a minimum. We were hoping to find a minimum area at this position. So what we need to do is find the second derivative. And so the first derivative was determined and then rewritten in a variety of different ways. So I'm just going to jump over from here and find the second derivative. So d squared a over dx squared. This 2 is acting like a coefficient, so I'm just going to copy that and then consider the derivative of 1 minus 60x squared. And, well, the derivative of 1 is nothing. Minus 60 over x squared. So that minus 60, again, acts like a coefficient, and the derivative of 1 over x squared. In my head, I'm thinking of this as x to the negative second power, so I need to multiply this by negative 2x and then decrease the negative second power by 1, so that gives me negative third power, and now I've got 2 times 120 times x to the negative third, which is 240 over x to the positive third power. And I don't need to perform a full second derivative test on this. What I would like to know is what happens when the second derivative is evaluated at an x value of the square root of 60. Well, that would be 240 divided by the square root of 60 cubed. And off camera, I performed that on my calculator, and that's about 0.5164. And the numerical value isn't all that important. What I'm worried about is whether it's positive or negative. And in all honesty, if I've got a positive number that's cubed, that result will be positive. And I've got the number 240, which is also positive. So without doing any math whatsoever, I would recognize that this derivative is greater than 0. So when we have the behavior of a function that encounters a first derivative that's 0 and simultaneously the second derivative being positive, which implies concave up portion of the graph, if the function is concave up where the first derivative is 0, we have found a minimum. And that's exactly what we were after. In order to minimize the area of this garden, or the combined area of the garden, to minimize the area, x would have to be the square root of 60 meters in length, and y would have to be, and I'm going back up to my constraint here, y would have to be 30 divided by the square root of 60. And if your work crew doesn't quite understand the precise values, well, certainly you can compute the decimals at this point. And we would have approximately 7.7460 meters by 3.8730 meters. Now, notice that we did solve for x and y here, and x and y represent the dimension of the garden itself. It does not represent the length and the width of the combined area. So we do have to be careful with that. And if we were checking our answers, if we wanted to take it one step further, if you're still not convinced or if you need further proof that this is a good answer, you could check, does 30 equal x times y? And certainly in this case it does. Does the square root of 60 times 30 divided by the square root of 60 equal 30? And certainly, yes. The square root of 60s will cancel and we've got 30. So again, x and y, the dimensions of the garden, not the combined area. And as it turns out, the instructions were very clear in asking for the dimensions of the garden, not the combined length and width of the total area. Let's try another example. This one's pretty fun. In this scenario, a boat is out on the ocean and it's 4 miles away from the nearest point on the shoreline. So here we are out on the boat, and we've got to get to a restaurant that's 6 miles away horizontally along the shore. The options that this person faces are, well, traveling straight to the shoreline and then traveling along the shoreline to this restaurant for a total of a 10-mile distance. Another option might be this person could travel in the water straight to the restaurant. Now that would be the shortest distance, but that may not be the fastest route to get there, because if we look down below, we're told that she can walk 3 miles per hour and she can row her boat at 2 miles per hour. And so the question becomes, at 2 miles per hour the entire way in the water, is that going to be faster than traveling along the shortest distance in the water, but then the longest distance on land? And as you can see by the diagram, or I bet you can infer by this diagram, that neither one of those is the fastest, but instead there's a position somewhere along the shoreline that will produce the shortest amount of time in order to arrive at the destination. And that's really what question A is asking us to do, is to minimize the travel time, and there's our clue for our objective function. The objective is to minimize the travel time. So we need a formula that involves time. As a side note, I threw this information on the screen. It's not immediately evident, but it's necessary for this type of work. In science class, you probably learned about this formula, that the distance that you can travel is equal to the rate at which you travel times the length of time that you travel. Distance is equal to rate times time. And so if we wanted to modify this, we could say that the rate at which you travel is equal to the distance divided by time. But similarly, we can also say that the time that it takes you to travel is equal to the distance divided by your rate. Now, our instructions here say to minimize time. That's our objective. So if our objective is to minimize time, then we're going to need a formula that involves distance and a rate. Well, if she just stayed in the water the whole time, we can actually address this because she's using one distance and one rate of travel the entire time. But in this particular case, we've got two occurrences that are happening. We've got to minimize the amount of time that she spends in the water in conjunction with the amount of time that's spent on land. So we really have two distances, d1 and d2, and both of those have different rates. So here's our d2 rate, let's go ahead and use r2, rate 2 and rate 1, because the rate in the water correlates with the distance in the water. So as far as our objective function goes, we might say something like this. Time is equal to distance divided by rate 1 plus distance 2 divided by rate 2. So there's our objective. Now our constraints might not be so obvious, but if I can offer any clues here, I would recommend that you look for the numbers in the problem. Much like back here, the numbers in the problem were that we were dealing with 30 square meters and additional width of 1 and 2 meters, and those values all went into our constraints. Same thing's going to happen in a problem like this. The ocean is 4 miles from the nearest point on the shoreline, so that's a limitation. That's a constraint that we have to deal with. Additionally, the total distance between the straight line from the boat and the shore is a total of 6 miles. Now, what would be helpful here is if we recognize a variable. We don't know where along the shoreline is going to be the best. She could aim for this position and essentially take this pathway. She could take this, or aim for this position and take this pathway. She could aim for this position and take that pathway. We don't know where she's going to land. And so this position is a variable. It slides left and right, somewhere between this position and this position. So what I'm going to do is I'm going to label this position, or this distance, x. So from perfectly perpendicular to the point at which she lands on the shoreline, we'll call that x. And therefore, this distance here, we will consider as 6 minus x miles. And now to provide some additional information, or perhaps clarity with the equations, we'll then say that y is equal to 4 and that x, well, this is our unknown. And our constraints then are simply this, that y has to equal 4 and that x has to be some value between 0 and 6. But really, that's a discussion of a domain restriction. Let's see if we can incorporate this notion of distance and rates into a better constraint. So let's talk about d1 for just a second. d1, this distance along the diagonal, if you recall, would be equal to the square root of x squared plus y squared. Because much like any right triangle, a squared plus b squared equals c squared. And if I want c by itself, I'll take the square root of both sides. So for distance 1, we might say that this is equal to the square root of x squared plus y squared, but we know that y is fixed to be 4, so I'll say that distance 1 is equal to x squared plus 16, or 4 squared. Distance 2, on the other hand, doesn't require any special calculations. This second distance along the direction of travel is just simply going to be 6 minus x. It is worth noting that rate 1 is 3 miles per hour. Oops, I'm sorry, it's actually 2 miles per hour in the water, rate 1. And rate 2 is 3 miles per hour on the shoreline. So these objectives, especially these two here, are going to be helpful for us to rewrite our time objective function. So I'm going to write t this way, t of x, because the time that it takes to arrive at her destination is dependent upon the position x, where along the shoreline she rows towards. So d1, of course, is the square root of x squared plus 16 divided by, we've got 2. And for, to conserve some space, I'm not going to include my units, but this distance is miles, and the rate is miles per hour. Miles divided by miles per hour will generate a unit of time in hours. So that's good. Distance 2, 6 minus x divided by 3. And now we've got our time function. This is our objective for which we can find the derivative. Now, finding the derivative in this format can be a bit challenging, but I'll share with you a trick that's often used. When we see fractions with numerical values in the denominator, a lot of times we'll treat those fractions as products of simpler fractions. So instead of taking this numerator dividing by 2, we'll just take 1/2 times that numerator. Additionally, that numerator is a square root, and a lot of times we'll think of radicals as a rational exponent. So I'm going to use that as 1/2. That'll make it easier for when I apply the chain rule to this derivative, and I won't have to worry so much about the quotient rule with multiple derivatives in the numerator. I'll do the same thing for the second component. I'm going to treat this as 1/3 times 6 minus x. And if you really wanted to, you could distribute this 1/3 in and call this 2 minus 1/3 x. And I actually think that might be a pretty good idea, so I'm going to do that now. So 6 divided by 3 is 2, and negative x divided by 3, we can call that minus 1/3 x plus 2. All right, so now derivative time. I'll change the ink color here so that we know that we're talking about a derivative. And I'm going to use the chain rule for this first one. I take the derivative of the outside and I keep the inside, so I want 1/2 times 1/2. So there's a 1/4. We leave the inside function alone for the time being, and we reduce the outside function by a power of 1. So 1/2 take away 1 is 1/2. Then we immediately have to multiply by the derivative of the inner function, which in this case is 2x. The derivative of negative 1/3 x is minus 1/3, and the derivative of 2 is 0, so nothing there. Might be nice to combine this 2x times 1/4, and that's going to leave us with 2x over 4, or 1 over 2x. And I recognize that this negative power pushes this group back to the denominator, and it returns back to a radical form again. So I'm just going to write this as the square root of x squared plus 16 in the denominator. And we still have minus 1/3 on the outside. Oops, I made a mistake here. This 2x is in the numerator, so I wanted not the x in the denominator, but the 1x in the numerator. Sorry about that. So mentally I was doing 2x over 4, and that should be 1x over 2, not 1 over 2x. That was my mistake. I think we're in good shape now. And I'm sure there's some other algebra that we can perform to combine like terms, but I don't really think that's going to be necessary, because remember, our whole objective is to find when this first derivative is equal to 0, or when it doesn't exist. And if we've got this equation equal to 0, I can add 1/3 to both sides of the equation. And now if I've got a pair of fractions that are equal to one another, I can cross multiply. So 3x is equal to 1 times 2 times the square root of x squared plus 16. And I can divide by 2 on both sides and have 3x over 2 equals the square root of x squared plus 16. I think at this point I would square both sides to eliminate the radical, and that leaves me with 9x squared over 4 equals x squared plus 16. I don't particularly like denominators, so I'm going to multiply both sides by 4. Call this 9x squared equals 4x squared plus 64. I just did that to move this over. And now subtract 4x squared from both sides. 5x squared equals 64. Divide by 5, so x squared is equal to 64 fifths. And then take the square root, and we've got the square root of 64 fifths. The square root of 64 is 8. Square root of 5, I don't know what it is, so we'll leave that as a radical. And if that pains you to leave a radical in the denominator, sorry about it. I'm okay with that. We would likely reach for a calculator anyway to see what the decimal equivalent is. And as it turns out, 8 divided by the square root of 5, or when you have the rationalized result simplified, you're still going to get the same thing, which in this case is 3.5778. So this is a good sign because at the beginning we said that x should be somewhere between 0 and 6, and we think that the solution occurs right here at about 3.57 miles. We can verify this, or we need to verify this, to make sure that we found a minimum by using the second derivative. So I'm going to jump back probably to here, and I'm going to treat this line as our first derivative. So we've got t prime instead of 0. I'm thinking t prime equals this expression. So if I want t double prime of x, I should be able to find the derivative here. Now the derivative of 1/3, that's going to be 0, and that goes away. And in this particular example, I've got a quotient rule that I can deal with. Although now that I say that, to avoid the quotient rule, I might use this example here with a coefficient and an outside exponent. Then I can use the chain rule and I won't be quite so confused. So I am going to rewrite it though, just as a reminder, t prime of x, if I combine this 2x and this 4, 1/4, would be, oh, well that won't be quite so helpful, 1/4 x times x squared plus 16 to the negative 1/2 power minus 1/3. Darn it, it's not going to be a nice chain rule after all. We've got to do a product rule in here to find the second derivative. But that's okay. That's just the way it goes sometimes. Okay, I still like the chain rule instead of the quotient rule, but we've got to involve the product rule as well. We've got one function here, another function here. This derivative is going to turn to 0 at the end. So let's do the product rule. The derivative of the first times the second function plus the first function times the derivative of the second, which is going to be negative 1/2 x squared plus 16 to the negative 3/2 power, because we're reducing this exponent by 1. We immediately multiply by the derivative of the inside, which is 2x. And this second derivative could be evaluated and should be evaluated at the result that we had identified down below. All right, and that was 8 over radical 5. So if I evaluate t double prime at 8 over radical 5, that's going to be 1/4 times 8 over radical 5 squared plus 16 to the negative 1/2 power. So, we're dealing with a positive number result here. We've got a positive plus a positive, and then 1 over that square root. So that whole expression, this whole expression is going to be positive from here to here. To that we add 1/4 times 5 over radical 8. That's a positive expression. But I think when we substitute here, we might end up with a negative result, and that's unfortunate. 8 over radical 5 squared plus 16. Yeah, that's unfortunate because we can't guarantee that the result is going to be positive or negative. This component, when it comes out to be negative, I don't know what the number is, but when it does come out to be negative, guarantees that this entire component is negative, whereas this entire component is positive. And what we don't know is what's going to happen when we sum a positive number and a negative number. Sometimes that's positive and sometimes it ends up being negative. Now, if the magnitude or if the absolute value of this was less than the magnitude of this, and if we could show that, then the sum would end up being positive. But if this magnitude or if this absolute value is larger than this one, then our end result would be negative. So all that to say, performing this work by hand without the use of a calculator can be a bit challenging. I know it's tedious to do all of the algebra that's gotten us this far, but it would be really nice to be able to answer this without the use of a calculator. And off camera, I did execute this. I did compute t double prime at 8 divided by square root of 5 and ended up with a slightly positive number. It was approximately 0.04079. So it's positive. It's greater than 0. Therefore, when the first derivative is 0, our t prime was 0. Therefore, t prime was equal to 0 when t double prime was greater than 0. So we've got a flat spot in the graph that is concave up. So we found a minimum. And that's exactly what we wanted. We wanted to find the minimum time that it takes to get somewhere. So we found it now. And evidently this 8 divided by the square root of 5 is the minimum position. Or I should say is the position that minimizes the time that it takes to get to the restaurant. And if it wasn't abundantly clear, we'll just go ahead and state it here. The position that she needs to aim for is at 8 divided by square root of 5, or 8 radical 5 divided by 5 miles east of the boat. I think this would be a good place to stop in this video. I know there's a part B to this question, but I think I'll save that one for class. This time around, we have to solve for the unknown rate at which she rose in the water that would end up making it faster for her to row directly to the shore. So in other words, if she could row faster than 2 miles per hour in the water, how fast would she have to go so that she wouldn't have to approach the shoreline at all? But we'll talk about that one in class next time we see each other. Thanks for watching.